Hey, welcome back, class. Towards the end of the week now, Thursday is a last Chapter 11 review sheet before the Chapter 11 assessment tomorrow on Delta Math gets released. So just going to work through a couple of problems here. And of course, as always, if you have any questions on anything, I'll be available at office hours tomorrow morning from 8 to 8:30 on Friday. And you can also message me anytime through Edmodo or email me if you have questions. All right? All right, so we'll get going here. Looking at the first question, it's an inverse variation question. So normally I would say this is the one where you set up as the product of the two sets of values, except it's inversely to the square of y. So because of that, we have to now add that square component to the y value. So x is inversely proportional to the square of y. X is inversely proportional to the square of y. So that's one wrinkle that we hadn't seen prior in some of the practice questions. It doesn't really change much in terms of how you compute it. It's just don't forget to add that exponent in for the y variable. So in this case, we get when x is 3, the y value is 4, but that's going to be 4 squared. And then it says, find the x value. So we're looking for that second x value when the y value is 5, and that's going to be squared. So again, this turns out to be 3 times 16, so that's going to end up being 48, and that's going to equal 25 times your x2 value. So you divide by 25, and you get your second x value is going to be, 48 divided by 25, or I think if you write that out, that turns out to be 1.92. So you can write 48 over 25 or 1.92. Either one is okay, and that's your second x value. All right, so that's not too challenging, probably based on what we've done before. Here's another review question based on some polynomial graphs and some rational graphs. So we're just going to work through, again, kind of itemizing what some of these things represent. Remember, this is going to be in the form of a times, and now what we have to do is fill in all the factors that come from the x-intercepts. So there's one of the roots. So it's a double root because it bounces off. So that's going to be an x plus 1 squared. Here's another root at the origin, and it goes straight through, so that's a single root. So it's like x minus 0 or just x. And then here's a third x-intercept, and that's going to be, again, a double root since it bounces off, so x minus 2 and then squared. So we start out with that as our setup, and we're going to now substitute in another coordinate as best we can to work through the different values. So notice that it gives us this coordinate of 1 comma negative 8. So we go ahead and plug in negative 8 for the y, here's your y value, and x as 1. We get a times 1 plus 1 squared times 1 minus 2 squared. And so as you work through that, you'll get negative 8 equals a times, and then working through this is 2 squared, so that's 4 times 1, and this is negative 1 squared. So that's going to turn out to be positive 1, negative 1 squared. And so this is negative 8 is equal to 4a. And if you divide by 4, you get a is equal to negative 2. So since a is negative 2, it makes sense because if you notice, it's going down to the right in the long run behavior. So if we go back up to here and write our equation, it's negative 2 times, and then this is going to be an x plus 1 squared times an x minus 2 squared. There's your final equation for that. You can check it out graphically, make sure the table values matches up. Going over to here for the rational functions graph, okay, a couple things that we can use here. We know it's going to be a fractional format. I see some vertical asymptotes here. So I know that there are going to be 2 vertical asymptotes, which means I'm definitely going to have factors in the denominator for each of those. This one is at negative 4. So since x is equal to negative 4 and x is equal to positive 4, this is going to be a factor of x plus 4, and this is going to be a factor of x minus 4. So I know I'm going to have 2 factors in my denominator. And again, we're going to write our little fraction up here. So if we go down to the bottom here, we start constructing our equation. Y is equal to some coefficient, and I know that I'm going to have 2 factors in the denominator to account for those 2 vertical asymptotes. Okay, there are no holes in the graph, so I don't have to worry about any shared factors on top and bottom. So then the next thing I would notice is, well, I've got an let me use the correct color for that. I've got an X-intercept at -2 and at +2. So what that means is in my function, X-intercepts create factors on the top. This is going to be an X plus 2 and an X minus 2. And since I have no more holes in the graph, those are going to be all the factors that come up. Now, the tough part might be, what is this coefficient, right? So here, luckily, they gave us another coordinate, so we can plug this in for x and this in for y. And what we do, we get, when we substitute that in, we get 1/2 is equal to a times 0 plus 2 times 0 minus 2 over 0 plus 4 times 0 minus 4. So that means that 1/2 is equal to a times, this would be 4 over 16. So if we divide by 4/16, so cross multiply, you'll come out with an a value that turns out to be +2. So what that means is if we go back and replace that right here, and I write my equation out, let's go back up top. This is going to be +2 times x plus 2 times x minus 2 over x plus 4 times x minus 4. Now, if you look at the leading terms for this, let's go back down to the bottom. The leading term, I'll use that blue pen for horizontal asymptotes. If I plug in a 2 right here, my leading term for the horizontal asymptote turns out to be y equals 2 times x over x times x. Or in other words, it turns out to be y equals 2x squared over x squared. So therefore, y equals 2 is what my horizontal asymptote would be based on the coefficient a being 2. So if we go back to the graph here, that kind of makes sense because y equals 2 is right about here. And if we were to track that out, it does look like the graph is pretty much leveling off at about that horizontal asymptote. Okay? All right, next page question. Here's like a little bit of a word problem for this. So let's back out here. And so it gives us this function for the volume of pollutants in an entire reservoir. And this question is asking about what is the total amount of pollution that you can express as a function of time based on this reservoir value. So C of t would be equal to the percentage, the fraction of the reservoir's volume that consists of pollutants, so that's P of t, over the entire reservoir volume. So it's going to look something like that. Or in other words, C of t would equal 350 plus 30t over 12,000 plus 120t. Now, just be careful because in this case, don't forget that the leading terms are actually in the back end of this. So you have to be careful there not to think that the leading term is right here. The leading term is the back term. So if I were to highlight this, this is your leading term and your leading term. That's going to give you that horizontal asymptote for long run behavior. So just be mindful about that. That's going to help us when we get to some of the other questions later. In the first question, it says, what's C of 0 at time t equals 0? So C of 0 would just be 350 plus 30 times 0 over 12,000 plus 120 times 0. These are just 0, so it's going to cancel out. It's 350 over 12,000. So C of 0, which by the way is also the y-intercept, just turns out to be this number, C of 0, comes out to be 0.029166 repeating. So it says, what percentage is that actually going to represent? So as a percentage, we move it 2 decimal places. This is going to be approximately 2.92%, roughly, and that's rounded, obviously. So any question would, tell you specifically what to round to. Okay, so this is where you have the, decimal approximations for the percentages. So at time zero, that reservoir volume has a current pollution level of about 3%, roughly. Okay. Now, what happens as the time goes on and the number of pollutants increases as the volume of the reservoir increases? What happens to the overall level of pollutants down in the bottom? So we go down to here. What that's basically asking, if this were to continue for many, many years, that's kind of like describing the long run behavior. This is like as t approaches infinity. So what this is symbolizing is like the horizontal asymptote concept. So if we do that, I'll use that in blue. C of t is equal to 350 plus 30t over 12,000 plus 120t. The leading terms are the only parts that matter. These just drop out. They're insignificant. So as t approaches infinity, then C of t will approach 30t over 120t. And the t's are going to cancel. So this is about 1/4. So that's equal to 0.25. And so what that means is as time goes on, this is going to approach about 25% pollution level. And it should level off there, won't really rise above it. All right. Okay, next question. We go on to number 5. And here we have another sketch of a graph. So here we have that. And you know how we always like to look at things in factored form as well as standard form for different things happening. So if we do that in this case, you'll notice that in factored form, this is 2 times x squared minus 25. So that's going to be like 2 times x plus 5 times x minus 5. On the bottom, this factors again. So this is going to be like x minus 1 times x plus 3, and then times x minus 3. Here's your factored form. So as we're going through this, we'll see finding out all these different things and identifying them, then we'll sketch the graph, and I'll try to color code it like we've done in the past. Okay, so one thing you might notice right away is that there is clearly this, oh, I missed a factor up there. Sorry, there's an extra factor of x minus 1. I missed that one over here. There's this hole right here in the graph because we have a shared factor. So that right there is going to be that hole, right? So I'll cross this out, and this is going to be that hole that we always talk about when you have a shared factor top and bottom. All right, so with that hole being in there, let me rewrite the factors without the hole in it, or with that removable discontinuity. So it turns out to be 2 times x plus 5 times x minus 5 over, and then on the bottom would be like x plus 3, x minus 3. That's essentially what we're looking at with the hole removed. And we'll go back and we'll find out, where is that hole? We'll figure out where it is, and we can do that using the simplified expression and just plugging in the x value from the factor. We'll do that at the end. All right, so a couple things in the beginning. First thing is the horizontal asymptote. We need the leading terms, right? 2x squared times x, that's 2x cubed. And then there's a lot of other stuff. And then over here we have x squared times x, that's x cubed plus a lot of other stuff. But it doesn't really matter there. These are going to cancel. So for the long run behavior, this is going to approach y equal 2. So the horizontal asymptote here is going to be y equal 2. If we construct that, we can put that in here right away. Here's one of our boundaries. That's the horizontal asymptote, y equal 2. All right. We go to the vertical asymptotes. Well, vertical asymptotes, if you remember, right, those are the orange ones. Those come from the factors in the denominator, but not including any holes, which would be removed. So it's just the 2, and we have that one at x equals negative 3, and we have it at x equals positive 3. All right, so those are the boundary lines for our graph so far. So next thing we're going to do, let me write that in there. Oops, sorry. We have x equals 3 and x equals negative 3. All right, so now we have x-intercepts coming up next. Well, the x-intercepts come from factored form factors of the numerator set equal to 0. So we have 2 of those. So those are going to occur at negative 5 right here and at positive 5 right there. So those are our 2 x-intercepts. Okay. So we have x equals positive 5, x equals negative 5. You could also write that as 5 comma 0 and negative 5 comma 0. So any of those are okay. We have the y-intercept. All right, so to get the y-intercept, standard form usually helps a lot. In this case, we don't have it in standard form really, but we do know that the constant times the constant. So in this case, y would equal negative 50 times negative 1. That's positive 50 over negative 3 times negative 3. That's positive 9. So 50 over 9 is approximately the y-intercept. That's about 5.555 repeating. So this is like 0 comma 50 ninths. There's your y-intercept. So 5 point a little bit. Here's 5 in the middle there, 5.5. That's about where the y-intercept is, roughly. Okay? So we've got pretty much all the information solved. The only other thing we're missing is the whole. And we know that the whole occurs at x equals positive 1 because the shared factor, if you remember, was x minus 1. So x equals 1 is where the whole is going to be. Now, how do we find out what the y value is? Take the simplified form after you remove the discontinuity, and we substitute in the x value from the removed factor. So it's going to be 2 times, we're going to plug in a 1 plus 5 times 1 minus 5 over 1 plus 3 times 1 minus 3. And you'll notice, like when you work that out, that comes out to be a y value of 6. So we have a removable discontinuity whole at 1 comma 6. Okay? All right. So going on to our last question, the algebraic roots. How do you solve a polynomial with multiple roots, and we want to do it algebraically or find some algebraic method for it? So we try to factor it if we can. We do get a little lucky here because it has a GCF right in the beginning. So we can get rid of the x squared, and we're left with 9x to the third plus 12x squared minus 11x, and then plus 2 equals 0. So if we do our little t-chart right here, we already get 2 roots right off the bat. X squared has to equal 0, and 9x cubed plus 12x squared minus 11x plus 2, I want to solve that equal to 0. So this means if I take the square root of this, right, we get something like this, and it's a plus and a minus. So technically there's 2 roots there. So what that means for us is x is going to equal 0, but that's going to happen twice. I'll show you later on in the graph when we look at it. You'll see how the root actually is a double root and the graph bounces off at 0. So now we're left with having to solve this. So this is a bit of a problem because initially we look at it and we say, all right, well, that's not factorable the way it is. It doesn't work by grouping or any other method. So in the beginning, what we can do is we can take our calculator and we can just graph out that function. Here it is. I typed it out ahead of time. And on the Zoom standard window, you see a picture that looks like this. So I'm going to look for an integer root that I can divide out. Okay, so we already used the 0. So that was our double root that we just took a GCF out. But notice that there's another root here at negative 2. So I'm going to use that to synthetically divide out a root of negative 2. Okay, so I know that negative 2 is another root. I'm going to synthetically divide that out. All right, so here's the process now. We add straight down, multiply diagonally. Add straight down, and we multiply diagonally. We add straight down, and we multiply diagonally. And sure enough, it's what we expected. 0 comes out to be the final remainder. So now what we're left with is what this says, 9x squared minus 6x plus 1. And I want to solve that equal to 0. So if we go back over to here, all right, I'm going to take 9x squared minus 6x plus 1 equals 0. You have a lot of options to solve that. We talked about it earlier last week and a little bit with the review this week. You could use the quadratic formula since it's a second degree. You could do completing square as long as you get rid of that coefficient. I don't know why you would try that. You could also try factoring it because it does factor, but there's no guarantee that it will always factor. So the safe bet is probably the quadratic formula. In this case, if you were to do the bridge technique, this would turn out to be 3x minus 1 times 3x minus 1 equals 0. So if I show you the algebraic factoring method, this would be 3x minus 1 equals 0 twice. So you get x is equal to 1/3 and x is equal to 1/3. You actually get 2 of the same root again. Just like 0 was twice, this is also twice. So your final solution set to this, you get 0, and technically that's twice. You get -2, and you get 1/3, which is also technically twice. So even though there's 3 distinct x-intercepts, there's actually 5 roots. There's 2 here, 1 there, and 2 there. So just to go back to the picture, just to show you how it lines up. Right, now this is what you see initially. You might say, well, I can't really see the 0 and the 1/3 because on the Zoom standard window, it's kind of hard to see. So what you can do if you're interested, just to verify your algebra, we could kind of find out what's going on with this on a smaller window. I just hit zoom box, which is the ability to kind of find a picture frame around the x-intercepts. So I just framed in the x-intercepts, and I'm going to hit enter to blow that up a little bit. So there was the -2. Here's where it's going to come down and bounce off of 0, and then it's hard to see what happens there. So what I'm going to do, I can't see the 0 and the 1/3, like what's going on there. So I'm going to redo a zoom box feature, and I'm going to kind of zero in a little more specifically right around the origin to see what's going on at 0 and also at 1/3. Now, none of this do you have to do. This is more for your own peace of mind to see, and or actually explain why it's bouncing off 2 roots at 0, comes off the x-axis and bounces again at 1/3. And that's the reason why we have double roots at 0 and 1/3. Okay? So hopefully that clears that up for you a little bit. And if you have any questions, like I said, I'll have office hours on Friday morning, and you feel free to message me as well. All right? Good luck, guys. Talk to you soon.